For the next few weeks, we're going to look at the concept of models. This week, generally data models. Once we get our data model established, we'll go then learn some SQL and how to implement that data model.
Page 34 reviews the learning objectives for this chapter. It's always a good idea to look those over. In a nutshell, what we're going to be doing is learning what a data model is. It's your first step in developing your database design. And I want to emphasize how important it is to know that the business rules decide on what your database design will look like. In week 1, we discussed that different individuals working with data have different views of the database. This correlates here to the external view. The external and conceptual models both have a high degree of abstraction, and that means that you can design your model with no concern for what type of database or hardware that you will eventually implement it on. Using the terms from week 1, the conceptual model is that global view or schema, and the external model is the subschema or a partial view. This chapter over the data model is about how you will create the conceptual model of your database. You will interview the end users to get their user needs, and these are also called use cases. For example, the view of the accountant is different from the view of the customer service rep. In addition, people at the top of the business organization have a more global view, but if you only interview them, you're going to miss a lot of the detail. So you also need to interview the data entry person. Every user view is important. You're going to take those user views and merge it into your conceptual model. There's other things you can do to get the data. Besides interviews, you might also job shadow. You might examine current reports and forms. Here is an example of a very simple data model using an ER diagram. ER is for entity relationship. We have two entities, department and course. Notice that they're modeled in a rectangle. Inside each entity, we have some attributes or fields. So the entity behaves like a noun. It's a thing. And the fields and attributes describe that thing like an adjective would. In between the two entities, they are related. That's the relationship. The relationship has the term offers. That's a verb. So a department offers a course. We'll get into what these symbols mean in a little bit.
In this example, we see a use case for student registration. So what does a student need to do to register? And you'll see that we need a student entity, an enroll, I call it registration entity, a class entity, and a course entity. A different use case could be class scheduling. Someone else is doing the scheduling and they're not actually looking at an individual student. What they're looking at are rooms and what classes need to be scheduled based off of the courses that they have in their department and what professors they have to teach those classes. We need to make the model for class and course here merge into the model for class and course here. And this is how we keep building out our design. Have you ever heard of the parable of the blind people and the elephant? Well, they went out and touched different parts of the elephant, and one touched the trunk and said, "Oh, this is a really thick snake," because that's all that that person touched. And another touched the ear and said, "No, no, an elephant is a fan," because that's all it touched. You get the idea. And use cases are the same way. So everybody only sees their little piece of it, except, of course, the database administrator. Types of relationships. Again, a relationship is an association between the two entities. To determine a type of relationship, you're going to take one entity instance in one entity and say, how many related entity instances are there in this associated entity? And you have three options: one-to-many, many-to-many, or one-to-one. For one-to-many, notice our notation is going to be 1:m, many. Or in a different type of modeling, you might have one dot dot star for many. An example is a professor can teach many classes. So in the professor table, I grab any one professor, and what's the most classes can this professor teach? Is it one or is it many? That's all you ask. Okay, you're saying, is it one or is it many? Oh, a professor can teach many classes. Then you go to the other side. Let's go and look at classes. How many professors can be in this class? This actually is a business rule. So some colleges will say, well, the most professors I can have teaching Chem 101 is one. So I have one professor teaching many classes, and one class taught by one professor. It's a one-to-many relationship. Let's look at many-to-many. A student out at the student table. And let's look over at the courses table, and there's a whole bunch of records. A student can take many courses. And let's look at the other way around. I have a course, and how many students can be enrolled in that class? And that's many. So we now have a many-to-many relationship, which we'll write M:(N). Reason we have an M and an N instead of MM is they don't need to be the same number. So that just connotes they're not the same number. Or we have asterisk, dot, dot, asterisk in the other notation, which we'll get to. A one-to-one is a little bit more rare, but let's say we have an employee table and we have a car table for a company because a car has company cars, let's say. An employee gets at most one company car, and that's the rule, that's the business rule. Let's get one company car. Let's look at just one company car in the company car table. How many employees are associated with that? One. That company car may not go to 4 employees. Now these are again business rules, but in this case that would be a one-to-one relationship. Well, talking about business rules, the type of relationship between entities is a major part of database design. You have to do that. Talking about business rules, let's describe that. They are very important in deciding this one-to-one, one-to-many, and other constraints. A business rule is a brief, precise description of policies that this particular business that's implementing a database does. It creates and enforces the action for that organization's environment. And business rules are used to establish what entities are needed, what entities will have associations or relationships between them, and constraints. An example of a business rule determining a type of relationship. Let me give you an example of a business rule determining a type of relationship. This was mentioned earlier. A professor can teach many classes, but there might be a college that says, oh no, but for each class there can only be one professor. But a different college says, no, a class can be team taught, so a class can have more than one professor. Generally, when you're trying to do that, you're saying, is it one or is it more than one? Depending on the college, you might set up professor in the class entity as one-to-many or many-to-many. And the business rule determines that. Other examples of business rules are GPA ranges. So if I have an attribute called GPA, it can only be from 0 to 4. I'm not going to allow you to enter a GPA of 99. Then we cannot implement that directly in the database. Or sometimes you're going to have constraints that are enforced outside of the database design itself, but you want to make a note in the design that this is a constraint that you need to consider. And I'm going to foreshadow how these constraints are implemented. We have something called triggers in databases, and that is a program. So a trigger is initiated, or trigger is executed automatically when you modify a certain field. So a trigger is linked with a field. So you can have a trigger happen when a field like GPA is updated or when there's a new record added. And that trigger can then use if statements in your programming language to guarantee that the GPA is in that certain range. I don't know if you've done any event programming, but if you ever done JavaScript, for example, you have buttons, and those buttons will trigger when a user clicks on a button, it triggers the event handler. We don't really say it triggers it, but it's a similar idea. Clicking on a button makes code run. Adding or modifying maybe the GPA field makes the trigger code run. So I hope you see that similar businesses might have different business rules. And this is why a lot of database design is customized and not out of the box, because the database has to follow the rules of that business. Again, emphasizing the importance of business rules and the data model components. Business rules are how you're going to identify entities, attributes, relationships, constraints. When you're describing the business, if you hear a noun, you're going to think entity. If you're a verb, you're going to think a relationship among the entities. Now, relationships are bidirectional. For example, how many instances or how many records of the entity B are related to records in entity A. Then you got to go around the other way. How many instances in entity A are related to one instance of entity B? So you take one instance in, for example, appointment and say, well, how many related patients? Well, appointment can only have one patient. Then you go over to patient, you take one patient, how many appointments? Well, over time, that patient can have many appointments. So that would be a one-to-many relationship. Now, the relational model, we're going to get deeper into that next chapter. It's developed by E.F. Codd at IBM in 1970. So a relational database is based on the concept of a relation, a table, and it's a matrix. Matrix is another name for table of intercepting tuples and attributes, or rows and columns. That's what a table is, right? Rows and columns. Some terms. DML, data manipulation language. This is an SQL subset that allows us to access data. And you see the word manipulation in there. So we can manipulate the data. And then we have DDL, data definition language. And this is what the DBA is going to use after we get our data model. And this is what you're going to do. You're going to use DDL to create your entities or create your tables, and set the constraints and the relationships and all those building blocks we talked about earlier. Here is a relational diagram. It's from Access, and you will see two entities here, agent and customer. You will see the primary key. In agent is agent code, and in customer it's cus code. And you notice agent code is the foreign key. In Access, when they do one-to-many, the many looks like infinity in Access. So each of these are attributes. Here's relational notation. So sometimes what I'll do when I've got my data model, my ER diagram, I'll move that to relational notation. And then from here, I'll create the tables. So the ER diagram is that graphical representation, and it was developed by Peter Chen in 1976. It's been through several iterations of improvement, so there's multiple notations. So software that you can use to develop ER diagrams, I usually use Visio, but there are also online resources for developing ER diagrams. Here's an example of the different notations. I initially learned the Chen notation, named for Peter Chen. This is a very simplified model. We have a painter entity and a painting entity, and we have the relationship paints in a diamond, and we can see that's a one-to-many. Here's a many-to-many, and here's a one-to-one. Here in the middle, we have the crow's feet notation, similar, except now the many to many, except now the one to many is shown as slashes through the line relating the entities, and this is known as crow's feet because the many side looks like a little crow's foot. So this slash adjacent to the entity represents the one in the one to many, and we'll get to what these slashes means when we're talking a little bit more about ER diagramming. And here is many to many. We're only looking at the notation next to the entity, and here's one-to-one. And then finally, UML, class diagram notation. You may have done some UML if you took some object-oriented programming language, and we can use that UML for database design too. And here is where that one ... star is at. You're going to place it right here adjacent. So you'll see with the relational model, we have independent tables instead of a file where you have to specify that 30 bytes will be for the last name and 16 bytes for the first name. And if you ever change that, you have to rewrite all the programs. So now we have tables and we have columns. So you don't have to worry about rewriting a program if you change last name from 30 bytes to 35 bytes or 35 characters. And just the view itself is simpler. Thinking of a table, it's kind of like Excel, right? It's very easy to use SQL to do ad hoc queries. If someone asked me what month had the highest sales of toothbrushes, for example, I could go in and quickly query that. It's not a big program that I have to write because of SQL. In the old days before relational databases, you had to write a program to do that. Isolates the end user from the physical level detail. They only have their view of the data, and it just improves implementation. Management is simpler. It requires a lot of overhead and expensive DBMS for an enterprise system. It's just harder to learn unless you're trained with the tools to learn it. Most people are not going to learn SQL. So we have to write those programs for those people. Once we get the conceptual model, we're going to then create the internal model. So from here, you're going to write SQL. That's our internal model. Actually, in ER diagramming, we're going to list the fields here or the attributes here. And then from here, we then write the SQL. And that's what you're going to do when you're ready to implement the database. The advantage of SQL is it's an ANSI standard, which means that it should be implementable, if that's a word, to any type of database. So this SQL I can put in Oracle and create tables. I can put in SQL Server and create tables. It's a standard. Then after the internal model, again, the internal model is still independent of the hardware, but then we get to the physical model, and this is the lowest level of abstraction. So as you see, these models go from a very high level of abstraction. In fact, the users aren't seeing these entities. We're writing the programs to make accessing that data very user-friendly. And there's the next level of abstraction, a little bit lower because you're seeing it all. You're seeing everything and how everything relates. Then my abstraction's going down even more as I see the very detail of the contents and what type of data I'm going to allow those contents to contain. And our lowest level of abstraction finally is the physical model, and we're describing the actual storage media and the server it's on. The physical model is hardware and software dependent. It's on Oracle, on this specific server is how we view the physical model. So the relational model, what we're going to do in the next few chapters is at the logical level. We're not concerned with what specific database. But what's great about this is when you go out, start working with databases, what you're learning here is a standard. So it can go to any type of database. In summary, a data model is an abstraction of a real world work environment. And there are many types of data models. And data modeling requirements are a function of different data views that we're going to then develop for and merge together until we finally have that entire global view.